All right, thank you. So now we're about to start our next presentation. So our friend Pfaff is going to show us how he's made a DPDK powered Faucet router. Along the way, actually, here he's made a really nice tutorial as well. So I always get DPDK wrong, so I'm certain to learn something from myself. All right.
Thanks, Josh. All right. So, I have one correction to start out with. This doesn't really have anything to do with DPDK, but it does have. It is a kind of OBS Faucet tutorial, and the bit that I know about is OBS. I suspect that most of you guys, especially Josh, know a lot more about Faucet. So if I get something wrong, just jump up and yell at me. I can take it. This was kind of inspired by a tutorial I did at the OpenStack Summit in Boston back in May. And so there I was demonstrating OVN, and OVN is this network virtualization system that OpenStack can work with. And the trouble with OVN and OpenStack is that each of them has a couple of different layers, so that in the end, whatever you do in OpenStack translates through about 6 layers before you actually get to the data plane. That's pretty awful, and you really need a tutorial if you're going to figure out how what you do in Neutron and OpenStack actually affects packets. Faucet and OpenvSwitch, that's much simpler, but I thought, and so there's only about 3 layers. But I still thought that it might be valuable to go through that a little bit. So what I'm going to do is I'm going to demonstrate some of the features of Faucet, and then I'm going to show you how those translate down through OpenFlow and how OpenvSwitch interprets that. And I'm going to show off some features that you can use to debug not just how OpenFlow works, but how OpenvSwitch implements that in a decent high performance way. So this is actually in my GitHub repository, my OBS reviews repository. My guess is that by sometime next week, it'll actually be checked into the OBS tree. So if anybody wants to actually follow along and go through this, that should be very easy. So I'm going to skip over more or less the steps you need to get into it. I've already followed those. The basic step is that you need to compile OBS, and there's nothing special about that. You can just follow the instructions. We're not actually going to be using this with any physical devices or even with any of the I don't know, less physical, more virtual Linux devices. So you don't even need to have root on the system where you're doing this. You don't need to compile with DPDK or OpenSSL or even compile a Linux kernel module. So just follow the instructions if you're interested. Should be easy. Now, setting up Faucet, this was the bit that I had to figure out myself over the weekend. It turned out to be remarkably easy once I figured out I should just do the Docker method. So I just typed Docker build and a couple options and just waited a few minutes. Now, the bit of the instructions for installing Faucet that I ignored were the bits that said that I should actually create some system level directories for configuring it. I didn't want to mess with my system config. So what I did instead was to create a directory under my Faucet installation and then just give Docker run some options that mapped those files to where Faucet expected them in the Docker image. So that's the command you can do to run it. I've got a terminal down here where I'm actually going to run that command, and then a few seconds later we should have Faucet running. Let me see if it started up. Okay, yeah, it has. Now, what I haven't done at this point is put in any sort of Faucet configuration. Obviously I need to do that. So I'll explain what steps I'm going to go through. So first of all, I'm going to show how Faucet's switching support translates down to OpenFlow and then to OBS's data plane and the performance implications there. Then I'm going to add in some routing and show the same thing. And finally, I'll add a couple of ACLs and show how that works. I thought about adding a few more advanced features. I couldn't figure out what those should be. One that would have been really easy is IPv6. Should work almost identically to IPv4. So the layers that we've got in this system, there's really only 3 of them. The first one is Faucet itself. You configure it with a faucet.yaml file where I too always seem to insert tabs. But it lets me know awfully quickly that I did that and yells at me. So Faucet then translates its configuration down to OpenFlow and pushes that into OpenvSwitch, which speaks OpenFlow. So there's a couple of tools that we're going to use, and I'm going to demonstrate for observing what's going on there. The first one is OVS OFKittle. That's OVS's utility for working with OpenFlow. It has OVS in the name, but at least in theory, you should be able to use it with any OpenFlow switch because it does speak the standard OpenFlow protocol. I don't know how many people do that. I haven't received bug reports about it, so I'd guess not very many. I'm sure there's bugs. We're also going to use a tool called OVS AppKittle, and you can use that for various sort of maintenance and debugging features of OpenvSwitch. It sounds like it's OVS specific, but it's really just a very dumb JSON RPC interface. So if you preferred, you could use another JSON RPC interface or even interact with it through some sort of a program that isn't a generic one, but actually understands what OVS is doing. So I've talked about the Faucet layer, I've talked about the OpenvSwitch OpenFlow layer, and the third layer that I'm going to go into is the OpenvSwitch data path. So OpenvSwitch, if it didn't have this data path, it would be very slow because every packet would have to go through the OpenFlow tables. The OpenFlow processing in OVS is pretty slow. But the data path is a caching layer, and ordinarily the caching layer works quite well to accelerate the OpenFlow processing. Most packets don't actually hit the OpenFlow processing layer, and what we're going to go through is some of the factors that make that that caching layer work, so that after the presentation, I hope you'll have an idea of how to tell whether the caching is being effective and the sort of factors that influence them. So let's go into the first aspect here, switching. So I've got a very simple faucet.yaml here, and as you can see, what I've got is I've got five interfaces. Interfaces 1 through 3 are on one VLAN, VLAN 100. Interfaces 4 and 5 are on a second VLAN, VLAN 200. And then it didn't work if I didn't include a VLAN section. I don't know what it was good for though. So I included it and it worked. Actually, the other thing that may be interesting here is I set some long timeouts. Normally your Mac learning timeouts are, I think it defaults to 5 minutes. That's what you'd normally want, but I'll probably go on chattering long enough that my Macs will actually time out when I'm trying to talk. And then that would be inconvenient and embarrassing for me. And I'll probably do enough embarrassing things anyway. I don't need to add to that. So let's take this, this configuration file and then cat it over whatever I had there before. And then I'll tell Docker to restart Faucet. It shouldn't really be necessary to do Docker restart, but I kept screwing things up, and it wasn't clear to me whether that was my fault or Faucet's. So let's see whether it. Yeah. So we got this the same line here. It must have restarted. Okay. So one thing. So now let's see here. Okay, so now we've got Faucet running. It's expecting some switch to connect to it and claim to be data path ID number 1. We haven't actually done anything to start OVS. So the next step is start OVS. So I'm going to start it in this configuration called a sandbox, an OVS sandbox. And what this does is it's very much a dummy environment. You can use all the usual OVS tools, but it's not connected to any real interfaces. It's not connected to VMs. If I create interfaces, they won't connect up to anything real. So now, by default, there's nothing configured. So I have to create a bridge, add some interfaces to it. And so I'm going to run this nasty-looking command that does everything that I want there. So it's going to add a bridge, set its DPID. This really made me wish that I'd designed that so you could just type 0x1, but I didn't. So there's exactly 15 zeros followed by a 1 there. And then it adds some ports. I'm naming them P1 through P5. There's also some magic there so that P1 will always get OpenFlow port 1 and so on. Otherwise, they'd get more or less random port numbers, and that would also be inconvenient for this presentation. I'm telling it to connect to the local port where I told the Faucet to listen, and I'm setting the connection mode to out of band, which it's not really worth talking about. Just read the OBS documentation or harass me about it later. So I'm running all that, and so that should have started everything up. I didn't have to run those all as a single call to OBS vskittle. I could have broken it up however I wanted. It's easier to cut and paste if I can just do it all in one go though. So let's see what happened in Faucet. Let's look at its log. Okay, so it looks like the OBS switch connected. It found all the ports, so I think we're good. Now we can look at what OVS itself logged. See what happened here. So if we look back, then what we see is that it connected to Faucet, and Faucet asked it, "What features do you have?" And it said, "I've got these." And then later, Faucet asked it, "What ports do you have?" And it told it. And then soon after that, Faucet figured out what flow table should be there, so it deleted everything else that was in the OBS flow table. You can see the del there toward the end of the top line. And then it added bunches of flows. So that's all good. That's what we'd expect. And then at the end here, I've been talking for a while, so the switch and the controller have been getting really bored and asking each other, "Hey, are you still there?" "Yeah, I'm still there." So that's what's going on now. Okay, so we've got this OpenFlow table now, and the immediate question I ask myself is, what all these flows do, and what are they? Fortunately, the Faucet documentation has this nice little architecture document in it that says what each of these tables is for. And you can go look at that, but I found it actually very easy to just read the flows and figure out what they do. So if we take a quick look, then hey, we've got a bunch of flows, and you can read them raw like this. I found it slightly easier to read if I defined a shell command that adds a few options that make things slightly easier to read and removes common stuff that we don't care about, like timers and that sad Cisco cookie, and which is funny, but not every time. And so just let me define a couple other shell commands here because later on we'll want to save a copy of the flow table and then look at the differences because that's really helpful when you're trying to figure out what changed. So let's take a look at the flow table processed a little bit. So we've got flow table 0, and if you look at the docs, it says that this is for I think port-based ACLs. We haven't defined any ACLs, so all of these just recognize the packets that come in on a given port and go on to the next table. Then we've got flow table 1 for ingress VLAN processing. This has a bunch of flows that drop what I think of as inappropriate packets. So that top flow there, that's one that drops packets that claim to be from a broadcast address. You can't send from a broadcast address, so those are obviously invalid. It's not actually clear to me why it doesn't drop all packets from all multicast addresses, but that must be some sort of design decision.
We admitted the decision, so yes, that's a kind of decision we should.
Okay, and then there's a few other things there. You can see that it's dropping, gosh, are those MPLS packets as well? What's 88CC? I can't even remember.
Some CDP and some rich CPU, rich CPU.
Yeah. So anyway, packets that the switch does not want to deal with. And then we also have some flows that recognize packets that don't have a VLAN header because all of these ports are effectively access ports, and then tags them with the VLAN that they should have, so that internally we can process all the packets as if they were tagged with the VLAN that we've assigned to the given port. And so the weirdest thing here is how OBS says that it's setting a VLAN. So if you remember right, we gave these ports VLANs 100 and 200. So what the hell is this 4196 thing? So that's actually an artifact of how OpenFlow defines the VLAN vid field. It defines it with an extra bit at the top that just says that a VLAN is present. So any time you actually have a VLAN present, it's 4096 plus whatever the VLAN one number is. So that explains what we've got there. And then finally, we've got an entry here that drops anything that didn't match, and so effectively that's dropping anything that was already tagged with a VLAN header. Presumably, that's actually a feature to get rid of improperly tagged packets on ingress. Let's see. Table 2, not interesting because we don't have anything of that form. So table 3 is where it starts to get a little more interesting. What this is doing is effectively sending every packet that comes in at this point to the controller, and that's going to be for Mac learning, and we'll explore that with an actual experiment here in a minute. 4, 5, and 6 also not really used yet. Table 7 is again for almost the opposite of Mac learning. It's using the Macs that it's already learned, and again we'll get back to that in a minute. We've got some flows for broadcast and multicast in table 8. The broadcast ones are really easy to understand. What it's doing is that if the packet came in on port 1, for example, and it's supposed to be broadcast, then we send it to the other ports that are in the same VLAN. And similarly for a VLAN 200. Now, this could actually be optimized a little in the sense that OpenFlow, by default, if you tell it to output to the input port, it drops that. So you could collapse those top 3 flows into a single flow that just outputs to 1, 2, 3. But there's probably some other feature in Faucet that makes this not always the right choice. And so my guess is that that's just don't bother to optimize because there's not much value in the optimization. And these are just my guesses without ever looking at how Faucet works. So
that's right. You can also tell it that you would like it to use groups.
Ah, okay. Yeah, groups would also work for this. There's some stuff to do with multicast that I honestly just ignored. I don't like multicast. So, okay, this is basically statically analyzing the flow table. Quite boring, actually. So the thing I want to do next is use the OpenvSwitch tracing feature. And this is, in my opinion, a lot more fun. So let me just show you an example. So we can tell OVS, if I gave you a packet like this, what would you do with it? And then OVS will print out everything that would happen in that packet. So in this case, I'm giving it a very simple specification. I'm saying, if a packet came in on port 1, what would you do with it? And I didn't give it any more details, which means that you can't get a completely accurate answer, but it'll just assume that everything that you don't tell it is zeros. So this would be a packet with an all zeros Ethernet header and a zero ether type. So let's just see what we get. And so this is the output we get. That first line, that's just repeating what we told it again. So you can see the all zeros. And then below that, it's telling us this is what happens in each of the tables that the pipeline encounters. So in table 0, it's hitting this flow that has this particular match, and it's saying go to table 1, and then in table 1, that stuff listed there is happening, and so on and so forth through every flow table it actually hits. One interesting thing here is that you can see it's going to the controller. That's for Mac learning, like I said before, and we'll see that again in a minute. Toward the end, you can see sort of a summary of what would happen to the packet overall, and you can see that it's actually doing something fairly stupid. It's pushing on a VLAN and then popping it back off. It could optimize those together. Usually it does. I'm not actually sure why it didn't this time. And that's not a fault of the flow table. That's a fault of OVS's optimizer. The goal of OVS, one of the goals of OVS, is to allow controller writers to do what makes sense at a conceptual level, and then OVS should be able to make that fast. So that's not something I can blame Faucet for. Yeah.
I don't think you can optimize out the push and pop VLAN, because you might in table 7 typically use the VLAN for your Mac format. It's not in this case, but probably once you add an entry, you will see that.
Oh, you know, I think you're more or less right that because it's getting sent to the controller, it's sort of internally figuring that it has to leave that in because it needs it for the trip to the controller. So probably later on, after we've done the Mac learning, that'll disappear and get optimized properly.
You'll see no, it won't get optimized. You'll actually see an entry in table 7 which says on VLAN 100 this MAC address, send it to this port. So you need it. Well, you'll see it later, but once the controller action disappears, I think we'll see that the push and pop disappears as well. So another interesting message here is that OVS is telling us that if this happens a lot, it's going to be really slow because this packet has to be handled by the slow path, and any packet that goes to the OpenFlow controller that's going to happen. That's actually something where we're working on that for 2.9, but honestly, sending stuff to the controller is usually not much of a performance limitation. So now this was just a what if. It didn't actually send the packet, so Mac learning didn't happen. But we can add another option to this so that it does actually send the packet. And I want to show you what happens to the flow table when we do that. So I'm going to save a copy of the current flow table to a file, and then I'm going to run the same command. No, I'm going to run a different command. I'm going to run a different command that actually specifies a non-zero Ethernet source and destination address, and I'm going to add this flag at the end, -generate, that says actually do this stuff. Don't just simulate it. So I ran that, and it gave almost the same output with the 2 MAC addresses we gave it. But now, if we look in the Faucet log, and let's do that, we should see, yeah, it learned that MAC address. So we can guess that Faucet probably updated the flow table. So let's look at the differences between the flow table that we saved and the current flow table. So this is saying the pluses mean they're new flows. So Faucet added these 2 new flows to the flow table. They've got a timeout of approximately an hour, so that corresponds to the timeout that we told Faucet. And my talk's less than an hour long, so we shouldn't have any trouble with it expiring. So let's see here. So now let's try tracing in a similar way a packet that is supposed to go in the opposite direction. In other words, one that comes in on, say, port 2, and it's destined to the MAC address that it just learned is on port 1. So what do we see this time? This time, in the table 7, it knows just where to send it. Before, the packets we were sending were getting broadcast. On the other hand, this packet's own MAC address hadn't been learned yet, so the packet still got sent to the controller for that reason. So we can do the diff flows again, and now we've got both of these MAC addresses learned. So there's an entry for each of them in table 3 and in table 7. Now let's rerun this trace command and see what's changed. So this time you can see there's no note at the end about slow pathing, and that's because the packet didn't get sent to the controller because the MAC address has been learned at this point. So we've kind of demonstrated that the performance should be better once the MAC address is learned. So this demonstrates one of the factors that can severely affect OBS performance. If packets on a flow get forced to the controller, then that or to the slow path for another reason, that's going to be perform badly. So there's a few other reasons why packets can end up being slow pathed. For example, OVS has implementations of a bunch of networking protocols that you can optionally enable. You can turn off on CFM and BFD processing, LACP, STP, LLDP. All that happens in the slow path. Most of those are pretty slow protocols, so it isn't ordinarily a problem. But you can find out about this sort of thing if you notice a problem and you do tracing. Now, if we were running in a less simulated environment, what I could show you is that you can actually monitor the flows that are set up in the data path using OVS dpkittle, and then based on the information in there, you can take that information on flows that are in your running system, you can paste it right into that trace command, and then trace will tell you what probably happened to those packets. I say probably because it's possible that the state of the flow table changed between the time that you dumped the data path flows and the time you ask it to trace them. Yes?
I've seen some of the derivative user features that come from like this capability in terms of telling the flow of a packet through switch.
Yeah.
Kind of things. Has there ever been any thought about actually including time in this?
Oh, including time. What?
How long it takes to execute at that stage, so you would know.
So
You
that's.
would know how long it took, and then you would be able to trace like in a feed chain or something like how long it took to get through all the stages.
It's a good idea. I'm not sure how to do it. Let me think about that. It's because of the caching behavior, the time it takes to, for example, figure out the trace is it's a lot longer than the time to actually execute it later. My guess is that in an NFV chain, you'd have more time occupied going through each of the members of the chain than going through OBS.
Yeah, but it'd be nice to know.
Sure. Yeah, I'll think about that. See if I can think of something appropriate. Yes.
So again, now that we've learned everything, we still see the push and what we learned. I don't believe it will be optimized out.
Where do you see? No, you see at the bottom there.
1 and 7.
So the thing that you need to look at is data path actions. Data path actions means this is the cache entry that OVS is going to install, and this is just what it looked at while it was trying to figure that out. So this is saying that when a packet matches this cache entry, it'll execute exactly one action, output it to the destination port.
Oh, this is for the caching action.
Yeah.
Not for an actual pipeline execution.
Yeah, so OVS works a lot like a compiler. When a packet comes in, it figures out this is what we should do to packets that look like this. And so it's willing to put some time into optimization because it figures it'll probably amortize that cost of the optimization over a fairly large number of packets. Okay, so let's see. I already kind of talked about this concept of data path actions. OVS translates the OpenFlow actions that we encounter into these data path actions that are used for caching. Those data path actions are not exactly the same as OpenFlow actions. They're almost always something that's slightly simpler. They're easy for us to implement in multiple data paths. So I've mentioned the term data path several times. It's in OVS, it's a synonym for fast path. And so OVS has a few of these. There's the Linux kernel-based data path, where you use a specialized Linux kernel module. There's the DPDK or user space data path, which is implemented right inside the OVS source code. There's the Windows data path, which some nice people who use Windows have implemented. And then there's even an experimental BPF-based data path. And all of the optimization concepts that I'm going over today apply to any one of these data paths. So the performance for OVS, you have to really consider the multi-level cache aspects of how it works. So when a packet arrives at OpenvSwitch, it first arrives at the data path. So some of the data paths, which I'd say the most important data paths, they have what we call the Microflow Cache that it hits first. And so a Microflow Cache is a lot like a hash table that covers all of the important fields of the packet. So in essence, a Microflow Cache entry only covers one TCP connection, or actually just one half of it. In other words, the packet's going in one direction on the TCP connection. So this Microflow Cache, that's the key to performance for elephant flows, for flows where you've got a very large number of packets at a high rate that are in a single stream. Most your high bandwidth flows, they'll hit in that Microflow Cache, but most of your other packets will pass through into the secondary cache, which we call the Megaflow Cache. So the Megaflow Cache is designed to make high performance for packets that aren't in high bandwidth streams, but have a lot of, say, properties in common with other packets. So let me give you an example. There's a line here toward the end of the trace output that says Megaflow. And what that's telling us is that this is the Megaflow matching entry that OVS would use for this particular packet in this particular circumstance. So this is saying, and you can ignore these bits, they're not really relevant for us. This is saying that any packet that comes in on port 2 and has no VLAN header and has those particular Ethernet source and destination addresses and ether type 0, which makes no sense, but that we didn't tell it an ether type, so it assumes that. And any packet that matches on those fields can be processed the same way as this particular packet that we asked it to look at. Yes?
Why are you matching on the ether type? This should work for any random ether type. Shouldn't that be a don't care field? Or you have a fixed key for your Megaflow?
So it could be a don't care. In practice, it's a little easier to implement some bits of OBS if they can just assume that some fields are always matched. And in practice, you don't get packets with a wide variety of ether types. So there's probably 2 or 3 that actually matter. So OBS always matches on the ether type as part of the Megaflow. It's all part of our philosophy that make things fast, but be lazy if you can.
Could you send another packet with a different DL type, let's say 0800, identical packet, because this time it should not get punted. So I'd like to see what the Megaflow looks like then.
What did you want me to change?
Oh, just said, when you send the packet, just said DL type to 0800, some random.
Right, so this time it abbreviated DL type 800 to just IP, and then it added something at the end because there's special handling available based on whether a IP packet is fragmented. So we didn't tell it was fragmented, so it's going to assume that it wasn't. So it matches on that as well.
So this is the Megaflow entry. So can we so now we got 2 entries in the Megaflow cache, or?
We would, yes. This is the simulation is tenuous enough that I don't think that we can really dump the Megaflow cache. Okay, so if it yes.
I might be getting ahead of you, but you made it sufficiently ambiguous to say whether or not the Megaflow was. That's the Megaflow that it would use. Does it always install a Megaflow on each match?
So that's kind of an implementation detail, but currently it always installs a Megaflow entry unless there's such a high rate of installation of Megaflow entries that it figures that that there'd be more cost than value. So there's some sensitivity to system load. Okay, so we talked about the Microflow cache. If it misses, it goes to the Megaflow cache. If it misses there, it goes to the slow path. And then the slow path will typically install into the Megaflow cache. And probabilistically, at least when you get a packet that hits in the Megaflow cache, it may also install a Microflow cache entry. The DPDK folks in particular love to tweak what the requirements are for installing Microflow cache entries. So let's see here. I think I might have already, I've already talked through a lot of this. I should remember to actually use the text I wrote.
Sorry, you define Microflow cache? Is that the multiple individual tables, or what's the definition of Microflow cache?
So a Microflow cache only matches on a full connection state. So for example, all the packets in half a TCP connection would match a Microflow cache entry. That really only comes into play for high bandwidth flows, where the Megaflow cache is very general, but it's more expensive to look things up in it than in the Microflow cache. So I know all this is probably kind of baffling. We wrote a whole paper about it. So you can now go and enjoy 14 pages of baffling, including detailed algorithmic descriptions. And that was the 2015 NSDI paper, just titled The Design and Implementation of OpenvSwitch. And most of the paper is actually about performance, because as it turns out, writing a switch is not very hard. Making it fast is the difficult part. So we've looked at how switching works. Let's up the ante very slightly and try to do a little bit of routing. So I've got a a replacement for the .yaml file here, and in a version that does some routing between our VLANs. So let's look at the top part here is the same, and then those VLAN definitions that I was complaining about had to be there, but were blank. Now I've added some routes. So for our VLAN 100, I've added a 10.100 network, and given the router the .254 in that network. And I've done the same for the VLAN 200, given it to 10.200. And then apparently this tells Faucet it's okay to route between VLANs. I mostly copied this out of the first hit on Google for like Faucet routing config or something like that, probably written by somebody in this room. So let's restart Faucet. And then I will tail the log to make sure that it was happy with the configuration. Seems happy. Okay, so now let's go back and see what changed in the flow table. And the first time I did this, I was really amazed that the flow table really hadn't changed all that much at all. Routing seems to fit into this Faucet table remarkably gracefully. So what we've got is there's some new flows in table 3 that take ARP packets and direct them to table 6. Which is presumably where Faucet is going to deal with ARP processing for these router IPs that we've now invented. We can also see that there are flows to direct IP packets to some particular Ethernet address to table 4, and we can make this educated guess that Ethernet address is the one that the Faucet router took over. It's kind of interesting that it's actually the same Ethernet address for each of the routers. In theory, you could use different ones, but there's no particularly good reason not to use the same one, and I'm sure that it makes things a little bit easier in the source code. So we also have some new entries in table 4. And what it looks like is that they're there to make sure that the packets that they're routing are actually to a network or to an IP address that Faucet actually knows how to route. One of the interesting things here is that it duplicates these for each of the VLANs. That it seems like that could lead to a lot of duplication if you had a large cross product of VLANs and networks. OVS actually has a feature that Faucet could use to reduce that. It has something called the conjunctive match that allows to, instead of cross-producting, you would add. But honestly, my guess is that wouldn't be valuable for Faucet simply because there's probably a way to solve that in standard OpenFlow, and probably Faucet doesn't want to start using OVS extensions if it doesn't have to. And then finally, we've got a bunch of new flows in table 6. So it's got some flows that are sending ARP requests for the router IPs to the controller. Probably that's so that Faucet can process those ARPs. And then it's doing switching for other ARP packets, and what else? Yeah, either broadcasting them or unicasting them as it can. And then it's sending all the other IP packets to the controller, which is a little odd until you realize that it probably needs to be able to figure out what's the right MAC address to send these things to. It's probably going to have to do ARP resolution. So the other thing that I noted here that was a little odd is that it's got two flows at the same priority level that could both match a single packet. OpenFlow says that if you have a packet and it can match more than one flow at the same priority, then the switch is within its rights to just pick any one of them at random and use that. So in this case, if you had an ICMP packet, then obviously that could match IP as well. It's not a big deal here because they actually have the same action. So regardless of which one OBS chose, it would still work just as well. So I've given all my speculations. Now we can do some of these traces that I was showing you before to figure out what actually happens. So I'm going to go through 6 different steps here. So let's suppose that we have a host 10.101 that wants to send an IP packet to 10.201. So first, it's going to have to ARP for the router that sits between them, and then the router is going to send an ARP reply back to 10.101, and then at that point, the host knows the Ethernet address to send it to, so it sends it via the router. At this point, the router, it has the packet, but it doesn't know where to send it because it doesn't have the Ethernet address for the eventual destination. So it sends an ARP request of its own. Then the destination host sends an ARP reply. And then at that point, we're not actually sure what's going to happen because some routers will buffer a packet they've received while I do ARP resolution. So if Faucet does that, then the end host will get the packet. Some routers just drop them. So in that case, eventually the source machine will resend it, and then Faucet will pass it along. So let's try this. It's a little easier than it sounds, actually. But before we start, let's save a new copy of the flow table. So first step, the source host needs to send an ARP. For the router because it knows it needs to send it to the router. So I'm doing a more sophisticated trace command than I had before. By that I just mean I'm setting more fields. So the source address is one that I've decided on for this host. I could use any one I wanted. And ARPs are typically sent to broadcast, so that's the broadcast definition. Broadcast Ethernet address. The Ethernet type is ARP, which is 806, and then the rest of the ARP fields there are the correct ones to request the MAC address of the router. So what we can see here is that it goes through all the tables and eventually just gets sent to the controller. So that makes sense. The controller is going to be doing the ARP processing internally. So let's see. So what do we see in the Faucet log as a result? So we actually get 3 different messages here. So first of all, it's saying that now it knows that it can reach this machine that sent the request via that port. Second, it sent an ARP response back to that port. And finally, it learned the MAC. So let's see what kind of a difference to the flows table did that give us. So we've got new flows for the MAC learning. And those are the same sorts of flows we saw for MAC learning before. It's the flows in table 4 that are kind of interesting. We've got, they're both the same except for the VLAN. But what they're doing is they're matching packets that are directed to this host that was the source of this thing, and forwarding them, doing IP forwarding for them by, let's see, they set the VLAN, they set the Ethernet source to that of the router. They set the Ethernet destination to that of the host. They decrement the TTL, and they keep going. So this is how Faucet implements IP forwarding. Remarkably simple, actually. So we know that the router sent an ARP reply because it told us. So, and we probably want to be able to see that somehow so that we can make sure that it was what we expected. There's not really a way to do that for simulated packets unless we set up something special. So let's do that. We can adjust the OBS configuration so that packets received or sent by this simulated port get written to a PCAT file. So let's run that and then rerun our trace command. Once we do that, then we can see that this is the ARP reply that that Faucet sent to our simulated port, which is exactly what we expected. So for convenience, let's do the same thing for all our simulated ports because we'll want to look at some of those later. So now what's happened is our host sent an ARP request, it got an ARP reply back. So now it can send its IP packet via the MAC address of the router. So let's see what happens when we tell OVS to simulate that. So as you can see, what we've got here is a packet that's coming from our host with the host's IP address and MAC address, destined to the router's MAC address, and with the IP destination of the host we want to go to. We also set an IP TTL of 64. If we left that out, it would be default. It would be 0 by default, and that would cause all kinds of confusion. And probably that's the sort of thing I would do on the first try, but I wrote this down in advance. So, and then what we've got here is you can see that the packet ended up going to the controller. And presumably that's because Faucet doesn't know the destination MAC address of where this thing is supposed to go. So if the controller is working the way that IP networks normally do, it issued an ARP request and sent that to all of the ports in the VLAN where that destination host could be. And since we set up these ports, these files correspond to those ports, we can dump what went to those and see what ended up there. So yeah, we see there's an ARP request, and it's repeated it several times saying, where are you? And we can do it for port 5, we see the same thing. And then just for completeness, let's do it for port 3. That port 3 is on the VLAN 100, which is not the one that should contain this host. So presumably Faucet should not be sending ARP requests there. And indeed, it's empty. So everything has worked out the way we expect. Yes?
So we installed a field entry in both VLANs 100 and 200. So it would not be unusual to have, let's say, 10 different subnets in basically the same work. So we're going to install for each IP address as many entries as there are VLANs in that routing domain. It's pretty inefficient.
Well, that's probably a Faucet design choice of some kind. My guess is that if it became a big constraint, they'd come up with a more efficient way to do it.
Yeah, so at the moment we just like make it work correctly, and then we optimize it as we need to. So the first time around we just need to optimize it because it covers the use cases that we want.
Okay. Eventually you probably need a perfect struct, so you can have a single entry of that.
We will blessed with an abundance of optimization opportunities.
Frankly, it seems like Faucet follows the philosophy that I do: get it correct, then optimize. So if we're going to make Faucet happy, we need to send an ARP reply. So here's how we send an ARP reply for port 4 saying, here I am. And this is going to the controller too, because this is an ARP reply destined to that IP router's MAC address. Let's see here. And let's see what the Faucet log has to say about that. So it's saying that it got an ARP response. So now it's learned that MAC to IP binding. It also learned the MAC address in the same step, which makes sense. And then we can do the similar diff on the OBS flow table. And from here we can see that now the MAC and the MAC to IP bindings have been learned in both directions. So the question now is, did Faucet buffer that IP packet that was waiting for ARP resolution and send it on, or did it drop it? So to find that out, we can dump our port 4 PCAP file. If an IP packet shows up, then that's the one. And I threw an IP into that line, so this is just saying there were no IP packets in that PCAP file. Probably, I mean, it's possible that Faucet buffered it for a while and then after a couple seconds dropped it, but my guess is that it doesn't buffer them at all. It's definitely the easier way to implement this stuff. So let's resend this packet and see what happens. So in this case, we can see that it no longer goes to the controller. Instead, it's going out to our port 4, and the data path actions correspond to that. So the data path actions, they change the Ethernet source and destination, and then they change the TTL because we decremented the TTL. This is probably just some sort of optimization bug because there's no reason for OBS to reset the destination IP that's already there, and then it outputs it to port 4. So,
just as another on the earlier point, another reason for us not to. I'm not suggesting that this is what you're saying that we should do everything, but like if one thing to avoid for us to prematurely optimize is there's information in these flow entries that the data path can use to make a better decision than we can. So it might actually be, it sounds kind of paradoxical, it may actually be more efficient to have more flow entries because it may make the data path easier to do a better job.
Mm-hmm. Yeah. So, and then what was, okay, let's look at the Megaflow. So here's the Megaflow entry, and this is what's really important to look for in OBS performance. So we can see that the Megaflow entry matches any IP packet coming from that input port without a VLAN and with those particular fields. So that means that basically any conversations from this point forward between these two machines over IP will be covered by this, regardless of whether they're regardless of the other fields. So that's normally that normally will lead to good performance. Let me, in the last couple minutes I've got here, let me show something that, yeah.
Again, the TTL, if someone's messing with TTLs, you create one.
Mm-hmm.
Every TTL value.
Yeah, they could, but if people are messing with TTLs that way, then I don't care if they get bad performance. So very, very quickly in my last minute or two here, let's just add an ACL to our setup. It comes so close to catting over my log. So my ACL here, its goal is to drop all packets destined to TCP port 8080. So if you've been sort of following along, then naturally this would mean that OVS is going to put the TCP destination port into the Megaflow Cache entry. And that's going to be bad because it means that any packets for any fields other than TCP port 8080 are going to, each of those is going to create a separate Megaflow entry. So basically every TCP stream is going to have a separate Megaflow entry. That's not good because it means you get a lot of packets going to the slow path. let's see what actually happens. And let's do that by tracing a packet that goes to some port that is not 8080. In this case, I'm making it just plain port 80 instead of 8080. So let's ignore all the other crap and just look at the Megaflow entry. So OBS is actually a little smarter than you might guess, and it's saying that this Megaflow entry matches any packet that has 0 in the top 4 bits of the TCP port. So that means that, and so it can do that because 80 and 8080 differ in those top 4 bits. So that means that instead of sort of generating one Megaflow entry for every single value of the TCP port number, it instead would generate at most 16. And it could do better, because if you look, there are individual bits that differ there. It could just match on 1 bit. Its algorithm isn't quite that smart, so it matches on 4 bits. But it's still a big improvement. And there's a few more details here. If you wanted, you could go over them by reading the document. But I hope I've given kind of a decent overview of how you start out at Faucet, and it turns into OpenFlow, and then OVS takes that OpenFlow and manages to optimize it for the common cases.
In these applications, is there indication that it used actually the Megaflow entry instead of going through the tables?
The Megaflow and the Microflow Cache are meant to be transparent except for performance. So I've used up all of my time, and I'm happy to answer questions, but I probably should do it sometime after so I don't use up the next speaker's time. Thank you.